So let's write some balanced nuclear equations. Plutonium-242 undergoes alpha decay. So let's find plutonium on the periodic table, and I've reprinted a bit of the table so you can see it. There's our symbol for plutonium-242. The 242, of course, means the mass. Plutonium from the periodic table is element number 94, so we represent it like this. When plutonium-242 undergoes alpha decay, an alpha particle is spit out of the nucleus. We learned in a previous lesson that that is how we represent an alpha particle. It's 2 protons and 2 neutrons, so the mass is 4 and the charge is positive 2. We write a little alpha symbol to represent an alpha particle. And then the top, namely the mass, and the bottom, namely the charge, must agree. So on the left here, 242 equals 4 plus what? And the what in this case is 238. Similarly on the bottom, 94 is equal to 2 plus 92. And from the periodic table, right up above here, we see that number 92 is uranium, and we're done. Let's try another one. Gadolinium-163 undergoes beta decay. Here again, I've reproduced a part of the periodic table so you can see gadolinium right there in the center. We're going to represent gadolinium-163 as is shown here, where the atomic number of gadolinium is 64. So a beta particle, you recall, is represented by a 0 on top, a -1 on the bottom, and then a little beta symbol. And that's of course because a beta particle is a fast-moving electron that's spit out of the nucleus. It has virtually no mass, which is why the 0 is up, and it has a charge of -1. So let's make sure that we have the mass balanced. 163 is equal to 0 plus what? 163, obviously. And on the bottom, 64 is equal to -1 plus 65. So this element is number 65, which we see as terbium. Let's try this one. Carbon-11 is produced after a beta decay. So there's carbon right there in the middle of that bunch of elements. And here, carbon-11, it says, is produced. So it needs to be represented on the product side, not the reactant side, as the previous 2 examples were. There's our beta symbol. So what must we have started with? Again, the mass and the atomic numbers need to be equal on each side of the equation. So here we have 0 plus 11 equals 11 for the mass on the left, and -1 plus 6 equals 5, and from what's shown at the top of the screen, that must be a boron atom. Let's do one more. How many alpha decays and how many beta decays occur when californium-252 decays into thorium-232? So here we see californium is element number 98, and thorium right here is element 90. So here's how we tackle this. Whenever you're asked how many alpha decays and how many beta decays, you always start with the alphas. And that's because in alpha decay, the mass changes, but in the beta decay, the mass doesn't change. So here we can see that the mass started at 252 and it ended up at 232. Well, for each alpha decay, the mass drops by 4. So how many alpha decays must have occurred for the mass to drop from 252 to 232? And hopefully you can see that that is a drop of 20 mass units. So we're going to need 5 alpha decays. 5 alpha decays drops the mass from 252 to 232. Now, we talked in a previous lesson, and we showed on the previous slide, that anytime you undergo an alpha decay, the atomic number drops by 2. So, in 5 alpha decays, by how much must the atomic number have dropped? And that would be 10. If it drops 2 for every alpha decay, and there are 5 alpha decays, the atomic number must have dropped by 10. Well, look on here where it says, where we have californium. If we started at an atomic number of 98, if we drop 10, then that takes us to 88. But each beta decay will bring us up 1 atomic number. So to go from an atomic number of 88 to where we want to end up, which is 90, we need 2 beta decays.